Bang! Hello everyone, my name's Logan and welcome back to the lecture hall. For today we are covering section 11.2, series, because again, I didn't want to do trig sub. So, series, what the fuck are they? Honestly, I don't know. Just kidding, I know, that's what this video is about. A series is of this notation. It may be this big E, this big sigma, n, or from 1 to n, ai, and that's equal to sigma of just an, and essentially what this means is just you're adding them up, all the terms of a sequence. So it's just the sum of every single term in a sequence. That's what a series is. So if we go from 1 to n, that's going to add up the first n terms. We can also have infinite sums, so we would have this denoted as same sort of deal, except from I equals 1, then it would go to infinity, ai. And then this essentially, this means it's going to add up every single term. So a1 plus a2 plus dot 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 dot, literally all the way up to infinity. To expand on our notion of infinite series, we kind of have to look at kind of what they mean and just give another explanation of them. So given that n from the I guess sigma from 1 to infinity, and essentially that's adding all your numbers up to infinity, we're going to let Sn denote the partial sums. So what does that mean? Well, Sn is going to be the series from 1 to n of ai, and that's just going to be the first n terms. So not an infinite series, just a finite series of the first n terms. Well, a sequence Sn is convergent if the limit as n approaches infinity of Sn is equal to s. And so essentially, if our sequence Sn, which is our sequence of partial sums from the series, this sum of an, if that converges at a limit, if it converges to s, then our sum, this, will actually be equal to s as well if this sequence Sn is convergent at the limit. So we can think of this notation essentially as this is the same thing from 1 to infinity as just taking the limit as n approaches infinity of I equals 1 to n, where n goes to infinity, of an, or ai, and this is equal to the summation from I equals 1 to infinity of ai, and if the limit of the partial sums converges to s, well then this would be equal to s as well. Now we come to the notion of a geometric series, and essentially what this is if we have the sum of ar to the n, where the only thing that's increasing each time, I guess I should say n equals 1 to infinity, or I guess 0 to infinity. And so essentially what's increasing every time is going to be the power on this r, so then it's a plus ar squared plus blah blah blah, all the way to infinity. So the partial sum, this Sn, is going to be equal to a times 1 minus r to the n divided by 1 minus r. And then if, well, a r to the n is convergent if r, the absolute value of r, is less than 1, and this sum will be add up to a over 1 minus r. Why does that make sense? Well, if we take our Sn, and we know that the limit of the sequence Sn is going to be equal to the sum, or I guess equal to the series of ar to the n. Well, if we were to just take the limit of this as n went to infinity, if r is a small number, less than 1, or I guess the absolute value is less than 1, well, then we'd have 1 minus r to the n, and as n gets really big, well, it's going to be some form of decimal or some form of fraction. So then that number will get really, really small and converge to 0. So then we'd have a times 1 minus, well, 0 as we take the limit. So then we just have a times 1 over 1 minus r, which is just a over 1 minus r. So we have a theorem, and it states if the sum of an is convergent, then the limit as n approaches infinity of an equals 0. And this should make a level of sense, right? If our sum is converging to some number where we're adding up infinite amount of terms, well, if this final, quote-unquote, final digit of an, right, its limit is a number that's not equal to 0, well, our sum will increase infinitely, so we would not have a convergent sum. The other thing to note about this is this is not, this is a one-way implication. If an is convergent, then the limit as n approaches an equals 0. That is, the other way is not always the case. What do I mean by that? Well, if the limit as n approaches infinity of an equals 0, that does not mean that the series is convergent. We actually have a series 1 over n, which is divergent. And, well, but our limit approaches 0. So we need to realize for this theorem that it is a one-way implication. One other thing that we can say about this is we can take the negation of this. And essentially, the negation of this states that if the limit of an does not equal 0, or it does not exist, then our series is divergent. So that is a correct implication. We essentially negate this implication statement and say not this, then not that. And that's essentially true, and we can pull that straight from our theorem. So we know immediately if our limit does not equal 0, our series can never be convergent. If our limit equals 0, we actually have to do more work to understand and see if our series is in fact convergent. Now for the final theorem of this video. It states that if an and bn are convergent series, then, well, 1, the sum of an, the series of the sum of an plus bn is equal to the sum of both series an plus bn. The series of the difference of an and bn is equal to the sum of an minus the sum of bn. And if we have the series c, where c is a constant real number, with c is in R, and then c times an, well, this is just equal to c times the sum of an. And so that's everything I wanted to cover for the lecture portion of the video. Let's transition to some practice problems. So for number 7, it says, find the first 8 terms of this series, or the partial sums, find the first 8 terms of the sequence and try to determine if the series is going to be convergent. Well, we know if we just plug in, we start with 1, we plug in 1, well, that's going to be 1 because sine of pi over 2 is 1. Then we plug in 2, well, that's sine of pi, that's 0. And then sine of 3 pi over 2, that's negative 1, and then 0. We know how sine works, and then it'll be 1, and then 0, and then negative 1, and then 1, 2, 3, 4, 5, 6, 7, 8. We know it's going to be that. And then what do we notice? Well, this series, it goes from 1, if we were to add it up, that would be 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. And so it doesn't convert, our partial sums don't converge to anything. So, in fact, this series would be a divergent series. And for a bigger part as well, this sequence itself would be divergent. Moving on to number 15, previously in number 7 we saw a sequence that did not converge, and so when a sequence does not converge, it is completely impossible for the series to converge, and we know this from our theorems that we've done. And so now we have number 15, and it says, well, an equals 2n over 3n plus 1. And we need to determine if the sequence and resulting series from that sequence would be convergent or divergent. So, how do we do this? Well, we first need to figure out if the sequence is convergent, and then if it is convergent, figure out what it's convergent to, and then if it's 0, then we have to do some more stuff. So we take the limit as n approaches infinity of 2n, 3n plus 1, and then so we do it based off the power rule of the variables. And what do we mean? I mean, not power rule as in derivatives, but if the top power is greater then it's divergent. If the bottom power is greater, then it converges to 0. If the power of the variables are the same thing, then you just take the lead coefficient of each of those and divide the two. So we know this is n and this is n, so that's both n to the 1. So then this means it equals 2/3. So then the sequence is convergent. I guess I should have said CONV, but convergent. Now we're like, okay, well, it converges to a number that is not 0. So then what does that mean for our series? Perfect, you're right, if you guessed. Our series is divergent because we are just going to be adding up, essentially once we get to like the millionth and one term, we're just going to be adding up 2/3 and 2/3 and 2/3, and that's just going to diverge to infinity. For number 19, we are given a sum, an infinite sum, if you will, and we need to figure out if this is convergent to something, or if our sum is going to be convergent or divergent. And we are like, okay, well, how the hell do we do this? Well, we should probably turn it into a series, because if we can turn it into a series, we can do some series tests on it, and bada boom, bada bing, we get convergence or divergence. So we look at this and we're like, okay, 10 and 2. We're going to look at the first ones. We're like, okay, well, 10 is equal to, or I guess, negative 2, or I guess positive 10 is equal to negative 2 times negative 5, or something like that, right? Well, then we're like, okay, well, what about 2, or 10 and 0.4? 10 and is equal to 0.4 times 0.25. And then we're like, oh, wait a second, this is 5, and then 25. So then it's like, oh, it kind of looks like we have a power series here. But I'm not totally sure. So, how do we figure this out? Well, what would we need to divide 10 by to get negative 2? What would we have to divide 10 by to get 0.4? Well, we'd have to divide by 5, negative 5, positive 0.25, and if we actually do this as well for this one, that's going to be 125. So then we see, okay, well, we start with 10, and then we're going to just multiply by 1/5 to the n. And then we're like, okay, is it 1/5? No, it's going to be negative 1/5 because, it has to be negative 1/5 because it's alternating. And then we're like, okay, well, this sum is going to be from n equals 0 to infinity. And then we're like, wait a second, this looks exactly like our power series. And then we have to see, well, is the absolute value of 1/5 less than 1? Because if it is, then it's convergent, and we know what it's convergent to. Well, it is. 1/5 is, in fact, less than 1. 0.2 is less than 1. So then, this is just going to be equal to, well, 10 times 1 over 1 minus r, so 1 minus r. R is negative 1/5, so 1 minus plus 1/5, which is equal to 10 over 6/5, which is equal to 50 over 6, which is 25/3. And we find that our series is going to converge to 25/3. Alright, that is everything I wanted to cover in today's video. Thanks for watching. Please give me critiques, like if I'm doing a shit job or you don't like the colors I'm using or something. Please tell me in the comments, because I'm trying to get better at this thing. And I have a lot of fun doing it, and I'm on a real schedule now. So I want to get better. Write some comments. How can I make my videos more interesting? What do you want me to cover rather than just doing calculus? Let me know. As always, thanks for watching. My name was... As always, thank you for watching. My name was Logan. Have a great day.